Okay, so in this video, what I wanted to do was go over how the different quadratic functions and some of the cubic functions transform in the C3 character table and proving that they transform as they do. So of course you can look this up in the character table, but where does this come from? And all the math should work out. So we're going to go through that in this video. So in my C3 character table derivation video, we showed that the function z, the linear function z, transforms as a, and x and y transform together as this sort of weird function e, irreducible representation e, which consists of complex numbers. Okay, it has characters that are complex. And we went over, the nomenclature for this. This is actually Euler's formula. You're gonna have to we're gonna have to expand this out using Euler's formula. So we'll do that in a bit here when we derive some of the other d orbitals. So what are the other d orbital functions we care about? Well, z squared. Well, since z is ones across the board, z squared is also going to be, it's like 1 squared across the board, so it's going to be ones across the board. And we can put that xz and yz are also going to transform together like xy, because if we're timesing something by z, which is ones across the board, it's just going to be the same thing. But what about x squared minus y squared and xy? And do those transform together? Do they transform as a or e? Those are our other, two functions for the 5 d orbitals, right? We have z squared, xz, and yz, x squared minus y squared, and xy. So we have to remind ourselves how these transform. So the identity, that's not interesting at all. It's not going to get us anywhere. So I'm just going to skip that one, right? Identity, if we test the function xy, xy is going to go to xy. If we test the function x squared minus y squared, it's going to go to itself. So let's start off with the C3 operation. What does that do to the function xy? Well, to answer that question, we need to remind ourselves what happens to x and what happens to y. And so remember that had to do with, we had to use the rotation matrix, the 2x2 rotation matrix. And if we do this in radians, we have cosine 2 pi over 3, negative sine 2 pi over 3, sine 2 pi over 3. Whether or not there's a negative here depends upon which side there's a negative on. You can have the negative here or the negative here, depending upon where you do counterclockwise or clockwise rotation. The math will work out either way, so it doesn't really matter. And then our last element here is cosine 2 pi over 3. And so what that gets us is actually, let's just write that out in a matrix solving for these various trigonometric functions. Cosine of 2 pi over 3 is negative 1/2. So x is going to go to negative 1/2 x. And then sine of 2 pi over 3 is root 3 over 2. So we're going to get that's we have a minus there, so minus root 3 over 2y. So x went to negative 1/2 x minus root 3 over 2y. X cannot be described, the result of x being rotated 120 degrees, C3 rotation, has to involve both x and y. So that's why we keep things together in a 2x2 matrix here. And same thing with y. Sine of 2 pi over 3 is root 3 over 2 x this time, following our matrix multiplication rules. And we're going to have plus root 3 over 2. Sorry, not root 3 to 2, we're cosine here. That is negative 1/2. So minus 1/2 over y. So that's how x and y transform. So how xy is going to transform is we just plug in what we got for x, that top part of the resulting matrix. And we're multiplying what we got for y, the bottom part of that matrix. And then we have to FOIL this out. And so we're going to get negative root 3 over 4x squared minus 3/4 xy. That's going to be one term. These two terms multiplied by one another. Plus 1/4 xy. That's negative 1/2 x times negative 1/2 y. Plus root 3 over 4, excuse me, y squared. That's negative 1/2 y times negative root 3 over 2y. Okay, and then from here, we can combine these terms. So we're going to have the negative 3/4 and the positive quarter xy come together to form negative 1/2 xy. And then we can also factor out a negative root 3 over 4 and get x squared minus y squared. So this is very interesting. Just like x could only be defined in terms of x and y as a result of the C3 operation, here xy can only be defined in terms of xy, a linear combination of xy and x squared minus y squared. So right away, this actually is sort of the end. You could just right now say, well, the only character on the character table that matches this is e, because there's a value of 2 here, and it shows two functions transforming together, 1 plus 1. It's broken up into subcomponents, right? But it's telling us that xy and x squared minus y squared transform together. Now, this isn't rigorous, right? And you could imagine that there's some functions that, don't transform purely as one of these irreducible representations. Maybe they transform as a plus e or something like that. So in order to show that, hey, this is actually transforming as e, we should carry on here. But it's giving us a clue that these are going together. And so the next part of this is that we're going to have to ask the question, well, how does x squared minus y squared transform? And so again, we're going to plug in our transformation for x under C3. And this time we have to square it. And then we have to minus it by our transformation for y and square that, right? So we're doing x squared minus y squared. So again, we're going to have to FOIL these things out. That first term there is going to get 1/4 x squared plus root 3 over 2 xy. Basically, we have 2 root 3's over 4's xy's that combine together to give us a root 3 over xy. And then our last term is the two terms with the y's. And so that's going to be 3/4 y squared. That was root 3 over 2 y, negative of that, times 1/2 y. So that's the x squared component. Now we have to FOIL out this other component, and remember that there's an extra negative sign there that we have to take care of. Our first part is going to be a negative 3/4 x squared. Then we're going to have a negative 1/4 y squared and a plus root 3 over 2 xy. And so we can combine like terms here, and we end up getting negative 1/2 x squared plus 1/2 y squared plus root 3 xy. That was the root 3 over 2 xy plus the root 3 over 2 xy. And now we can factor some things out. So we can factor out a negative 1/2, and that allows us to get something times a linear combination of x squared minus y squared, and then plus a root 3 xy. So again, we got something that's a linear combination of x squared minus y squared and xy, just like we did above. And so that's great. And so now what we can write here is a matrix, just like we did for xy, but now of xy and x squared minus y squared is going to be equal to the transformation matrix that describes this is going to be, the resulting transformation, we're going to times this by a 2 by 2 matrix. And we know now what that 2 by 2 matrix is, because we wrote it out here. So xy went into -1/2 xy. So we put a -1/2 there, and a -√3/4. And then x squared minus y squared went into a √3 xy and a -1/2. So again, just to be very clear, when we multiply this out, we get the results that we just got before. So this is where this came from. We get -1/2 xy minus √3/4. This is just matrix multiplication, right? The first column times this row, x squared minus y squared. And then we get √3 xy minus 1/2 x squared. Now, the important part here to get the character is we take the trace of the matrix, or the sum across the diagonal, the character of the matrix. And so that gets us that the chi for the C3 operation, the character is -1/2 plus -1/2, which equals 1. And so equals -1, sorry, -1. And so how does this help us? Well, you might be looking at this and thinking, I don't have a -1 anywhere here. I have these weird e components, right? And so this is then where you have to remember that what we just came out with was the combination, the combined. So what we basically figured out was -1 was this e value plus the what we call the complex conjugate e star of it. So the sum of this, right? If we do this for the identity, just as a simpler example, for the identity operation, we're going to get out a 2x2 matrix that looked like that, right? xy went into xy, and x squared minus y squared went to x squared minus y squared. We take the sum across the diagonal, and we're going to get character of 2. So chi of e equals 2. Where does that 2 come from? It's 1 plus 1, right? So in order to check that this makes sense, we have to see that e plus e star is equal to -1. And if it is, we're very happy. And so that's sort of the last part of this derivation for the C3. So let's just do that. And what is E? E is defined as the E, a different E. Okay, it's unfortunate. I don't know why they use the value of E in this character table here, but sometimes they do. Sometimes they use epsilon, which I like better. E to the 2 pi I over 3. So that's what this E symbol means, is E to the 2 pi I over 3. Well, Euler's formula tells us that that equals, remember, Euler's formula tells us that just to be clear, E theta I equals cosine theta plus I sine theta, one of these crazy, beautiful math formulas. So this is going to equal cosine 2 pi over 3 plus I sine 2 pi over 3. And what does that equal to? Well, cosine 2 pi over 3, we've been down this road before, equals -1/2, and sine 2 pi over 3 equals √3 over 2. And so we're going to have plus √3 over 2i. So that's what E is equal to. Okay. And so E star is just, so that equals E, which I know it's unfortunate that it's not this E, it's just a different symbol E. But E star is the complex conjugate of this. And all that means is we make the imaginary part of the complex number negative of what we had before. So it's just going to be, this part stays the same, the real part stays the same, -1/2, minus now √3 over 2 plus times I. And so then we can see that E plus its complex conjugate, E star, is actually just equal to -1/2 plus -1/2 which equals -1, which is exactly what we got here. So E star plus E equals -1, which is what we found the character to be. So we proved that xy and x squared minus y squared transform together, and they indeed have these characters. And so they transform as E. And so we could do the exact same thing with this value here. The only thing that's going to change is that all of these now are going to become cosine 4 pi over 3 and sine 4 pi over 3. But everything is going to end up looking pretty similar. There's going to be some small changes. We're going to have positive signs here just because of how the trigonometry works out, but you're going to end up with getting a character again. When you do a 2 by 2 matrix, you're going to get a character again, this time of C3 squared equals -1, and that's going to tell you, hey, E star plus E, we know from this math, equals -1, and so that'll further confirm that you have the right symmetry here. But this explains why you have the quadratic formula. These quadratic functions transforming like this. We could go further to look at some cubic functions. Some easy ones would be like z cubed. Well, that's just 1's cubed, so that's going to transform as a. If you do other ones like x times any of these quadratics by z, like xz squared and yz squared, those are going to go together, or xyz and zx squared minus zy squared, those are going to go together and transform as e, just because you're multiplying by -1. So more complicated ones to figure out are going to be like xy squared and x squared y, but you could do it with very similar sort of math as I showed here. So that's it for this one.